my young friends to today's my presentation of on toll station. Uh, so already, I think I thank the PhD Engineering College for conducting, and I also congratulate them for conducting this important training program on toll station and drone and lidar, etc. Because what we see is that uh, the in today's scenario, if you go to the revenue office, revenue department, you'll see that even today also we are using the FPS system only. They are using the revenue chain only, and we have seen that a lot of our departments, government department, have procured toll station, but there is no assistant engineer or engineers who are capable of handling them. So I think this is a very good approach by building engineering college, where they are training the all the faculties of many engineering college throughout India. So I request that all the faculties in engineering college also conduct such kind of training programs for engineers also, and the consulting engineers also, that so that the technology will go all over the the cross section of the society, and everyone um, will be take benefit from this program. So I will right away start with my presentation on this toll station. So first, I have to tell you the various leading manufacturers of this toll station. I think many of you in this session may be expert in this field of advanced surveying, and many maybe in the very initial stages. So I have to see that my presentation will be very basic, so that even in the smallest entry level participant also will be benefited and have a thorough knowledge on this toll station and the concepts. So I'll be more concentrating on the concepts on which the toll station is working, so that we have different instruments. You can see that we have Pentax, and we have Sokia, Leica, Trimble, Nikon, Topcon, Horizon. So these are all very high-end instruments, and very reputed companies, all reliable instruments only. So if you see all the instruments, so all the instruments, they have different softwares, but the concept will be same. The formulas will be same. Like sin theta will be same all over the world. So like that, these people are also using the mathematical formulas and extras. So every concepts will be same. Only thing is they are using the different softwares. Okay. So coming to this, up to the different types of manufacturers of instrument position provided. So, Chuchu, Chuchu, Chuchu. Mm.
Sir, any problem from your side?
The screen is not moving. Someone has given or annotating. Screening is not going. Screen is not there. Okay now. Okay now. Okay. So so Applications of a toll station. So I have to give an introduction. So toll stations are used for high precision angle measurements, high precision distance measurements by optical electronic methods. It is used for computing the X, Y, Z coordinates of any point and determining the boundaries and areas of the properties. Then we have application of doing contour. We can nowadays we know that any architect will demand a, property and the contour of a property in a digitalized form. So that is the only possible way we can give that digitalized map is with the total station only. We cannot give that with the conventional instruments. So application of total station in preparing the contour maps, property maps, all are very important application. So nowadays we see that all the works, all the major works in the civil engineering field, we use the stakeout for staking out the giving the position of the columns. So I've seen all my students, wherever they are working, they are using only toll sections to give the mark out of the column positions and in all the roadworks also and the building also. We see that the extensive use of toll section in the civil engineering field. And the survey data collection for road, railways, canals, designing and everything is used here only. Mm, True. True. ಮೂವ್ ಆಗ್ತಾ ಇಲ್ಲಲ್ಲ ಮೂವ್ ಆಗ್ತಾ ಇಲ್ಲಲ್ಲ ಇದು ಕಮ್ಮ ಏನು
What 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 problem you are facing, sir?
that slides are not moving. I don't know why. Slides
Sir, you
are
can put your video off.
video off. Okay.
Yes, sir.
ಹ್ಯಾಂಗ್ ಆಗಿದೆ.
Or else you can also stop this presentation mode, sir. That will also be fine.
Because it is getting hanged,
Maybe you can stop presenting and re-present again, sir. Hello. Request the participants to wait for a few minutes. Sir is trying to join back. Sir, are you able to present it back? You have shared this. Sir, the same presentation is shared from our side. This is fine. You can start presenting, sir. Sir, you have to unmute. Sir, you are not done.
Okay, now
Yes, sir, you are audible to us.
actually that Cisco was not responding.
Okay.
Okay, just I will explain you with my.
Okay. Sir, you can put your video off. Only you can have your presentation on, sir. That will consume your more data.
Okay. No, data is not a problem. That this one Cisco it was hanging. Okay, anyway, I'll start with the presentation. So in this, okay. So what is a toll station and what it does? So here we can we know that this toll station has four components. This the first component is the EDM. EDM it will measure the horizontal and the sloping distances, and we have as in the here also we have the you can measure vertical and horizontal angles very accurately, because in this case we are not taking the readings in the theodolite. We take reading as main scale reading and the vernier scale reading, but here the vertical angles and the horizontal angles are scanned by a electro-optical scanning device. So here we can take a vertical angle or horizontal angle as less as 0.5 seconds. So we know that in the theodolite the smallest reading we can take is 20 seconds. Whereas here in the high-end instruments we can go up to zero point 0.5 seconds reading we can take here. So this is the second component. Third component is the microprocessor. So this total station has a inbuilt microprocessor and computer where all the computation of trigonometrical calculations, everything will be made by the microprocessor. And the fourth component is the memory. So all the uh, measurements which are taken on the field are going to be stored in the memory card of the device. So totally in this tool session, we have four components. One is the EDM. So EDM is nothing but it is a solid state emitter. So that is, it emits a infrared ray. So the distance is going to be measured by this infrared ray by traveling from the tool station to the reflector prism and then coming back. So the time taken for going to the prism and coming back will be computed in the microprocessor of the processor. So EDM is a very high degree of accuracy we'll be getting because of this EDM, and the work is very fast also. So initially we are using the tapes, so it may be a steel tape or inward tape for accurate measurements. So they are all now by the past histories. Nowadays this EDM only it has revolutionized the modern surveying. So we have four components. That is one is EDM, then the vertical angles and horizontal angles by optical scanning, and then we have the microprocessor, and last is the memory. So these are the four together are integrated to become a toll station. So here we can see that to build a toll station, we require a civil engineer, we require a computer engineer, and also for hardware, we require an electronic engineer. So when you integrate all these three engineering only, then we are able to get this, the instrument. So coming to the next part is the correction of the measured distance. So already we know that in the measurement of tape, we apply the pull correction, we'll be applying the temperature corrections and curvature corrections. So here also the microprocessor it is uh, having the facility of making the corrections to whatever measurements we are making by the toll station. That is, the infrared ray is the main signal which are going to use to measure the distance. So here we are going to, the instrument is going to make corrections on the prism constant, atmospheric pressure constant, and then temperature corrections, and the curvature earth corrections, and refraction corrections. So all these corrections are made by the microprocessor of the total station. So other things, regarding the applications what it does is we can take the elevation of different points. We can take there is some software, we can make use for finding the remote elevation measurements. We can make remote distance measurements. Then we can calculate coordinates of hundreds of point. So there are many, and there are many other applications. Takeout is there, pre-stationing is there. All these applications are there in this total session. So this is the main gist of a total session. So already you people, I think you know that by now, that total session has four components. One is the EDM, another is the measurement of vertical and horizontal angles, and third is the microprocessor, fourth is the uh, memory. So this all together makes one unit of total session. Then all the lengths which are going to be measured in the total session are going to be, corrected for the different this one, because in the array, what happens in the total session, we'll be observing sometimes when you are going to take readings in a very bright sunlight. So what happens? The ray will not come back. So you can see the display panel will be seeing unfavorable conditions. So we are unable to take the reading. So sometimes in a very hot condition and all, the rays are the quality of the ray will not be that good. So the whole system will reject to take the readings. So like that, we have this total session and its functions. So I would like to I like to I like to introduce you to the different parts of the instrument of total session. So we'll come to this. So here we see that this is the handle. So to carry this, and then this is the handle securing screw, and third, this is the data input output terminal. See, nowadays, what we, the very important thing is whatever data is stored, data is to be transferred to PC. So then only we'll process all the data which is collected in the processing can be processed. So here nowadays we have this SD cards which can be placed inside the tool session. So here we'll be having a provision for putting a SD card to collect or transfer the data from the instrument to the SD card. And then we have this is very, very important. I think this HI mark, this is what is HI mark. See, this is a very important thing you have to remember. See, this HI mark means what happens, you have to measure the height of the instrument. So I think I will explain you in the comparative way. So in the dumpy level, HI, how we find out HI? We find HI by taking a reading on the benchmark. Okay, so the benchmark RL will be 100. So staff reading is taken on the benchmark. Suppose if there is a 1 meter reading, so the HI becomes 101. So like that, the reading HI in the dumpy level is benchmark plus BS. So, but in this total session, we do not bisect a benchmark. So HI, height of instrument, is directly measured from the the ground point of the total session to this mark on the total session. This is a HI mark which will be almost parallel to the line of sight. So you can see this is objective, and the below we are having the eyepiece. So the line of sight will be coinciding with HI mark on the total session. So this is a very important mark. So the vertical height from your station pointer to the mark has to be fed into the computer. So this mark should not be carefully, and this
Hello,
mark.
sir. Sorry to interrupt. Hello. Sir, there is discontinuity in your voice. Can we put off your video, sir, so that it will not lose much data?
Okay.
There is discontinuity in your voice, sir.
Okay, just Veer Madam,
Your video can be off, sir. Your presentation is already clear.
okay. This is one lesson, the rest. So I'll put up this one so that.
Okay, thank you so much, sir.
I think I'm clear now. My voice is very clear.
Yeah, it is clear now, sir.
Hello. So, uh, so this HR mark is very, very important in the toll station. So, we have to get the HI. So we have to measure the vertical distance from the station point. Vertical distance from the station point to the HI mark is called as the HI. So this data has to be fed into the system that will be explained in the projects. So after this fifth one is the battery cover. So here we are going to put the battery for the energy, and then we have the display. You can see this is the display panel. So this display panel is a alphanumeric keyboard. You can see this is the part is the alphanumeric keyboard. And we have the function key here and the display. We can see it in this one. So I will in the further slide I'll show it very clearly also how the display panel is going to be looking. Uh, so after display panel we have this the try batch. So this is the try batch and then we have base plate, the bottommost portion. It is just like the threaderite only. You can just visualize this try batch and base plate as same as the threaderite only. And then we have leveling foot screws. So in the tool station also we have 3 foot screws as same as the threaderite. So the foot screws will be used for leveling the instrument, and uh, then we have here we have the circular bubble. So here in this circular bubble, we'll be using this circular bubble to approximately level the instrument. Okay, so there is a one circular bubble here, and then we have this display panel, and then we have this objective. So we know that this objective, the competition, we are not measuring the staff reading. We are not taking staff reading. Uh, ಹಲೋ ಕೇಳ್ಕೊಳತ್ತಲ್ಲ ಇದು ಹಲೋ 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 ಇಲ್ಲ ಹಲೋ ಹ್ಞೂ ಹ್ಞೂ ಕ್ಯಾನ್ ಕಂಟಿನ್ಯೂ ಹೇಳ್ಬೇಕಲ್ಲ ನೀವು ಚಾಟ್ ಮಾಡೋದು ಫೋನ್ ಮಾಡಿ So I'll continue my presentation. Sorry for the interruption. So after, so we have this objective. I was talking about the objective. So this objective here we are when you are this we are not measuring. We are measuring by infrared rays. So when you have to be very careful. You should not be in front of the objective when you press the button measure, or when the infrared ray is going to be emitted. You should not keep your eyes in front of the objective, otherwise a permanent damage will be happening to your eyes also. So this carefulness you should be careful in this regard. So next, after that we have uh, so here we have this in the handle. I'll show in the this one. We have facility to fit the tubular compass on this handle. So in the total session, we don't use the normal type of compass. We'll be using a tubular type of compass where only it will show the north direction. So this tubular compass will be used, will be fitted on this handle. And then next we have this optical plummet eyepiece. So these are normally not provided in the advanced instruments. Optical, we are using the laser plummet only. So next we have this. This is the horizontal screw. That is the horizontal screw. So here to turn the telescope in horizontal plane, so we are having this horizontal clamp. So it has two they have two adjustments are there, fine adjustment and the normal adjustments. So in the one bigger knob will be mainly used uh, for normal operation of the turning the telescope in horizontal plane, and there is a small knob, so that is used for the fine adjustment of turning the telescope in this. So that's the normal this one. This is the next we have this. This is a port. You can see this is a port where it is called as a communication port, where we are going to connect the toll station to the PC. So by means of a socket and this one, we will connect um, the toll station to the PC, and all the data can be transferred from this port to the PC. So there are two options nowadays we have to transfer the data from the instrument. One is by means of the SD card, and another is this port. So we have external power source. We normally don't have that in nowadays instruments. So we have one more level. So we have one is we have the bubble tube, circular bubble tube on the try batch, and one also we have a plate level fixed on this one. So this plate level and bubble tube are just like in the we are in the dump level and theodolite what we are seeing. That way we are going to adjust we are using this to bring the bubble to the center. So one more, we have this vertical clamp. So again we have uh, normal operating. So when we operate the vertical clamp, so we can move the telescope in the vertical plane. And also one more finer clamp also is available, with which we can make the fine adjustment of the telescope in vertical plane. So this is your eyepiece. So here, you have to understand this is focusing we can do by just turning this. We can focus the object. So eyepiece, here there are three options in the high end. In the high end, this one, toll session, we have three options. One is the manually we can operate the eyepiece to focus, and second thing is we have the mechanical option also, by which just by pressing the button, automatically the object which you are focusing will get focused. And third is auto option. So here there will be a green button there. So when you press the green button, automatically the focusing is done. And so normally when we buy a toll station, compulsorily it is better to take high-end toll station with the auto focusing only, because the toll station we are going to take hundreds of reading. So every time manually to operate the eyepiece, focus the object is very difficult. So it is better to buy instrument which is having a auto focus only. So next we can see here there is one device. It is called as this one called as component called as the collimator. This is called as a collimator. It's just like a just on the top of the gun we have a arrangement for focusing the target. So here also the collimator is used mainly to focus the object. So instead of going into the eyepiece and focusing the object, so it will be better first to focus the object by means of this collimator, because the time taken less will be less in this method. So after focusing by the collimator, then you can go to the eyepiece and focus it. So we'll see that if it is coinciding with the collimator, so obviously it will be coinciding with the eyepiece also. So this is the parts of the instrument. So this I can show you the real instrument here. So see, we can see now, I'll again explain you very in brief. See, now this is a handle, what we have told you to carry the instrument. So in the middle, there will be some arrangement made to fix the tubular compass. So as I told you, we have to buy in some toll station, they are going to give with the instruments, otherwise you have to purchase separately. So this is a device exclusively, this is a device, tubular compass is a device exclusively for toll station only. So there in this, we are going to, in this tubular compass, we can note only north, magnetic north only. So what is the importance of that, we'll be explaining in the further slide. And then we have here now in modern instruments, we have a facility for having a SD card in this socket, and then we have the battery assembly. And as I told you, we have the horizontal clamp for horizontal movements. So this is a fine tuning, and this is a normal tuning. So we have the vertical clamp, vertical fine tuning, and vertical normal tuning. So this is for the vertical movement of the telescope. So we have two clamps, but as in the we have seen in the theodolite also. So after that, we have this display panel. We can see here very clearly. So in this display panel, we have this portion of the display panel is called as the alphanumeric keyboard. Okay, this is alphanumeric keyboard. So we can give input, can input data, either numerical data or in the alphabetical data can be input into the this one display panel feeding. So we have a alphanumeric keyboard. Then we have this 5 are called as the function keys. These 5 are called as the function keys. And you can see they are also numbered, they are named like F1, F2, F3, F4, F5. So this total session is a Pentax instrument. So I'm not fixing up my presentation only to a single instrument. So that's why I am very particular of giving the concepts rather than fixing to some instrument like that. So if you use any instrument, all instrument will have a alphanumeric keyboard, and compulsory all instrument will have a function keys, and they are also given a name F1, F2, F3, F4, F5. And what functions will come on the display. So for what is the function? Suppose there is a, this function is measure. It means that measure is the function which you get by pressing the F1 button. So like that we have function keys, 5 function keys. And then this red button is there to the left here. What we can see is it is for shutting down the instrument and to on the instrument. Okay. To on the instrument and the shutting also, we have the same key here. And then we have this button is for illumination. If you want to have light in the display panel, we can see you can use the illumination button. And then we have this is the return key. So return means escape. This is the escape button. So just like in the computer, so if you want to come out of the program or the software app, so just if you press this button app, this escape button, so it will come off the software application or program. And then we have a green button. Here it is called as the laser button. So when you press this laser button, so already I told you we have one circular bubble here and we have a plate. So you can see there's a circular bubble, and we'll not use this circular bubble for uh, precise leveling of the instrument. We'll be using the electronic vial or electronic bubble for centering of the instrument, which is very, very accurate. So this electronic vial will be displayed only when you press the button laser. So when you press on the button laser, we'll see the electronic vial as well as one more ray will be coming down. It is the red ray is there, so it will be coming down. It's called as the electron laser plummet. So that laser will be using for establishing the station point. So this button is used for 2 functions. One is to give a laser plummet and to display the electronic vial on the display panel. So so this is, and the last button is it is called as enter button. So enter button just like it is in the computer. We see that when you, for example, if you input a data, say you are giving a value of sum as 1.5. So once you feed the data, after feeding the data, you have to press the button enter. Then only that data will be sent to the microprocessor, and it will be saved in the memory of the total session. So unless and until you press the button enter, that will not be endorsed by the instrument. So these are the display panel. So I'll be giving more elaborate in the other slides. This whole display panel I'll be explaining in more elaborate way in my further slides. So after that we have this is a power, and this is a battery charger. So this battery is going to be charged with this power and this battery charger, and we have this assembly to connect from the tool station to the PC. So like that we have the different parts of the instrument, and then we have come to this just like in the theodolite, we have 3 foot screws, for leveling the instrument. So the foot screws are used for 2 purposes. One is for leveling and another also for adjusting the center of the plummet. So plummet has to be exactly coincided with the session point of the pole session. So for 2 purposes we are using this. Um, so so this is the collimator, as I told you. So from the eyepiece end, you are going to focus and the object. So object is nothing but it is normally for torsion will be having the reflecting prism. Okay. So reflecting prism is, so when we bisect the prism, so we have to focus that with help of this collimator. Okay. And then only we have to see from the eyepiece and you have to finally focus the reflector prism. So this is a part of the instrument. So we know this is a telescope. This is the objective end. On the other end will be the eyepiece. So eyepiece will have the 3 focusing options. One is the manual, another is mechanical, another is the autofocus. So these are the part of the total session. So it's just like simple as transit theodolite only. Only thing is here we are using more electronics and the software are going to be written on this one. So the electronic, you can call it as the electronic transit theodolite also. So I made this display panel more legible. So you can see here we have the alphanumeric keyboards. Okay. So we can operate numericals and also we can feed the alphabets also. And here we have the on-off button, and then we have 5 function keys, and then we have the illumination, then we have the escape button, and then we have the laser. So it is for laser plummet for centering of the instrument, and another also will have the electric vial. So if you press that, we'll get that also will be shown in the further slide. So another is the enter key is there, which is very important for endorsing the feeded data. So this is the display panel for the so you can see here. So this function keys are also given as F1, F2, F3, F4, F5 also. See the relative to this function keys we'll be getting here. See, we can see this. F1 is having measure, F2 is having target, F3 is having 0 set. So like that we are having this. So so in the display panel, see we are going to see the readings parameters like horizontal angle. We have vertical angle, horizontal distance, vertical distance, and sloping distance. So there are totally 5 parameters we are going to see. So by pressing this F4 button or the display button, we'll be only getting only one vertical horizontal angle we can see. Again, if I press the display button, I can only see the required vertical angle, horizontal angle, and the vertical distance. So like that, the way you want to see the display, you can just operate this F4 button. And then we have this mode button. See, in this total session, we have 2 modes. In the total session, we have 2 modes. One is the reading mode, and another is the recording mode or the app mode. So, we can see here we are having this as a mode A. Mode A means it is the reading mode only. Here we can only take readings, just to bisect a prism and press the button measure. So it will give you the horizontal reading, will give the vertical distance, sloping distance, vertical angle, horizontal angle. So all these 5 parameters will be shown. So this is only read. It is not going to be recorded in the memory, or it is not going to be sent to the processor for any calculation work. So this is the read mode only. So in read mode, we have only, you can see vertical angles. We can take, suppose you want to have a horizontal angle between any 2 points. So just you can move the, telescope from left to right. So we can take the horizontal angle. So we can just, press the button measure, and then you can take the horizontal distance, vertical distance, and all the things. So I want to elaborate on this button, that is measure. See, almost it is a single button operation. I call this toll session is a single button operation here. Why? Because uh, when you press this button measure, so the EDM is activated. So what happens when you press this button measure? So the solid state emitter in the EDM will emit the infrared ray. So this infrared ray will go to the uh, um, prism, reflector prism, and then it will be reflected back, and it will be corrected by the toll session objective. So that, what we are doing here is, we are measuring the distance. So it means that whenever you want to emit the ray, you have to press the button measure. Okay. So normally maximum operations we are going to take this by pressing the button measure only. Now you may ask me what is the target. So coming to the target, see, you can see here in the right top corner, we are seeing P. What is this P? See, when you emit the ray has to come back. So the ray is going to hit the reflector prism. So there are three reflecting surface by which the ray is going to come back. So first is the prism, reflector prism, and second is the sticker, and third is the non-prism. So for high-end instruments, you don't require a prism. You don't require any prism or sticker also. Just if you hit any surface, a tree surface or any wall surface, the ray will come back and the readings will be taken. But the range will be very less. If you are using non-prism, the range will be very less. So in our department, we have a toll station which can give you reading up to 200 meter. Okay, very clearly up to 200 meter. Also, it is very important that when you are using the non-prism mode target, so if the surface is not plain, or if it is having undulations, so it may be possible that the ray will be deviated back. When the ray comes from the toll station, the infrared which comes from the toll station may be deviated to other directions, so it will not be received to the toll station. So that reading, so there'll be always a beeping sound coming in the instrument that the ray has not come back. So in that way, this non-prism, we call it as non-prism. Without prism also, we can directly take reading on the surface also. But the range will be very, very less. And this facility is only available in the very high-end instruments only. They are available only in the high-end instruments only. So this is very important, because if you are going to, if you are, see, just you have to press this button target, so it will change to S. S means sticker. Again, you press the button target, it will change to non-prism. It will be like NP or NO. Will be clearly seen on the top right hand of the instrument. So target is very important, because if you have put prism and you are going to take the readings, you will not get the readings. The ray will not come back. So when you are going to initially set up the instrument station, so this is we will be taking this as the setting up of the instrument. Okay. You have to set the target very carefully also. So we have this one more button. It is called as zero set. So if you press this button twice, the horizontal angle will become 0, 0. So if we are going to take a reading between A and B, angle, if you want an angle AOB, so what I can do is I'll just bisect A, and I want to make the reading 0, 0. So what I will do is I will just press the button twice. 0 set twice, so the reading will become 0. Then you turn the telescope to B, and directly you can take the reading also. But there is a very specific purpose for having this button, so that I will be explaining in the further class, in the further slide. So here, we have the mode button. So if you press this mode button, it will from mode A, it will change to mode B. So if you want to operate softwares, or you want to record the readings which are taken by the instrument, then we have to go for mode B. So you have to press this button, it will go to mode B. So I'm showing this display by a photo visualization. You can see that we're having 4 function buttons. We have the on-off button, then we have elimination, escape button, target, enter, and these are all the alphanumeric keyboard. So here also we see the 0 set. Okay, if you press 2 times, this becomes 0, 0. Now, so I want to exactly explain what is a toll session. So I already told you this toll session, the main component is the EDM. So to measure horizontal and sloping distance. Okay. So I told you when you press the button measure, okay, so we have a small state emitter. Okay, this small state emitter placed in the toll session. So this is activated by pressing the button measure. So what it does is it will give you a modulated infrared signal. So we have which is the ray? We have the infrared ray. So we are going to activate a modulated infrared signal. Okay, once you press the button measure. So by means of a small solid state emitter. So this ray will travel, and it will be hitting the prism reflector. So after hitting the reflector, it will come back to the objective, and that it is again the time phase after leaving the ray from the emitter, and then the time of collection is noted by the microprocessor, and that will directly give the distance. So the formula, see this, how the distance is calculated is there are 3 parameters for this. One is the frequency. So for a given infrared ray, the frequency is a constant. Then we have for a given infrared ray, the wavelength of that ray signal is also constant. So the only variable factor is the time phase. So the time taken for the signal to reach the reflector and come back. So that is the variable factor. So with these 3 parameters, the microprocessor will in a space of just a microsecond give you the display of distance between the instrument station and the reflector point. So like that, this is the principle on which the EDM is done. The EDM is framed so that we have a emitter, we have a collector, we have a the formulas relating to the wavelength, frequency, and the time phase of the time taken for the ray to go and come back. So this is called as the EDM. So in the high-end toll stations, we can measure up to 1.5 kilometers, that is 1500 meters, with an accuracy of 1.5 millimeter. So this is the highest accuracy you can see in 1.5 kilometer, just, the error chances are 1.5 millimeter. So in high-end, as I told you, in high-end toll stations, they come with, we don't have to, uh, bisect a prism, reflector prism directly. We can bisect and we can get the ray back by hitting the normal surface like tree surface and the light colored any building or any surfaces. But it also depends on the nature of the surface also. If the ray is deviated by the undulations, so we may not get. And also the range is very, very less. Just, in our, as I told you, in our lab, we have a toll station which may give only 100, 200 meters only. It is properly giving the readings. Otherwise, only the beeping will be seen, but no readings are seen if you go for a higher distances. So this is regarding the EDM. And coming to this is regarding the measurement of horizontal and sloping distance with the toll station, and then we come to measuring horizontal and vertical angles. See, we have seen in the transit theodolite. We have seen in the transit theodolite, we have a disc. It may be a steel disc or it may be a brass with steel coating. Disc is there. On that, the readings are calibrated. Which on the disc, and we take the reading as main scale reading and then the vernier scale reading. So what we see is in the transit theodolite, the smallest reading we can take is 20 seconds. I think everyone knows. But here, the system is very different. We can see that, instead of using the metal disc, we are having a rotating glass cylinder or disc. Extremely precise digital barcodes are etched on the rotating glass cylinders or disc. Okay, so the calibration is done with the barcodes etched on a rotating glass cylinder or disc. So the reading is done by means of an electro-optical scanning. So the readings are picked up by means of electro-optical scanner. So in this way, the accuracy or we can take vertical angles and horizontal angles as less as 0.5 arc second. So in high-end instruments, we are capable of taking a reading as small as a 0.5 arc second. So this is the accuracy and the capability of the instrument in taking vertical angles. And in the low-end instrument toll stations, it may be like 5 to 10 arc seconds. So this is regarding a toll station measuring the vertical sloping distance, horizontal distance, and taking the horizontal and vertical angles. So the most important thing is now, so now till now what we have seen is a toll station is mainly used for high angle measurements, high precision distance measurements, and other apps are there, so that will be read afterwards. So in this toll station, we know that it has 4 components to be explained, and the toll station is designed to make corrections of prism, atmosphere, temperature, curvature, refraction. Then we have many, the softwares. Many software apps are there in the toll station, so that I will just be explaining in the further slides. So the applications you can see, and we have components of the EDM